Early in our school days, we learned about the basic states of matter: solid, liquid, and gas. If you heat a solid enough, it melts into a liquid, and if you heat that liquid some more, it boils off as a gas. But not everything plays by those rules. Take wood, for example. If you heat up a wooden log enough, instead of melting, it catches fire and burns. And sometimes that's a good thing, like when we get a nice cozy fire during winter instead of a wet pile of mush. But why doesn't wood follow the same rules as water or butter or crayons? Let's break down why wood doesn't melt, except when it does. All molecules everywhere are vibrating all the time. And they vibrate faster when you add energy from heat. A solid substance becomes a liquid when its molecules vibrate fast enough to break out of their orderly arrangement. Those molecules start to slide past each other, and the solid loses its shape to become a liquid. The temperature at which this happens is called the melting point, and the transition between states of matter, like solid and liquid, is known as a phase change. Even in a mixture of a bunch of different chemicals, they all have their own melting points. For example, when ice cream melts, it's because the water ice is melting. There's less going on in the cream part. Part of the reason wood doesn't melt is because it's also made up of a mixture of chemicals. These include water, as well as the plant materials lignin and cellulose. Some of these substances have their own melting points, but others, like cellulose, don't actually have melting points at all. Cellulose is made of really long chains of carbon, hydrogen, and oxygen. The amount of heat needed to disentangle these chains and melt cellulose is so high that they hardly ever melt. Instead, the chemical bonds holding the chains together start to break apart, and the cellulose breaks down into different smaller chemicals before it gets hot enough to melt, per se. The molecules in cellulose still vibrate when you heat them up, like when you hold a match or lighter under some firewood, but since it's so tough for those molecules to slide past each other, they end up vibrating themselves to pieces. So when you heat up wood, giant molecules like lignin and cellulose start to break into smaller molecules, including water, carbon dioxide, formic acid, acetic acid, methane, methanol, hydrogen gas, and several others. Some of those new molecules are flammable gases. As they form, they escape from the wood like air out of a balloon, and on their way out, they catch fire and burn, generating more heat. And fun fact, the popping sounds you sometimes hear in a campfire happen when some of these gases get trapped inside a log and then explode out all at once. Not all of the new chemicals are gases though. Any that don't burn off or escape as smoke end up as ash or charcoal. The heat from the flames breaks down even more of the large molecules in the wood, and that releases even more gases which burn and generate more heat, which breaks down more molecules, and on until all the fuel is spent. Because the lignin and cellulose break down into other chemicals at high temperatures, burning a log isn't considered a phase change in the same way melting is. A phase change, like melting, has to be reversible. If you've ever stuck melty ice cream back in the freezer for a while, you know that it's still ice cream afterwards, if sometimes a little grainy and ice crystally. But while you might be able to refreeze water into ice, you can't unburn a log, right? Let's get a little weird for a minute. What if you didn't have to melt a whole piece of wood? What if you could melt just one of the many chemicals that make up a log? Or maybe just a couple at a time? It turns out that is a thing we can do under the right circumstances. It's called wood welding, and scientists and manufacturers can use it to stick 2 blocks of wood together without using glue or nails. For some time now, construction workers and furniture makers have been using glues or even melted plastics to join 2 pieces of wood together. But many of those adhesives give off toxic fumes, and some of them can cause cancer. So researchers have been looking for some safer, more environmentally friendly alternatives. Wood welding takes advantage of the different compounds that are already inside the wood. The technique uses the lignin at the surface of the wood as a type of glue. Normally, the lignin in wood is solid and not very glue-like at all. To turn it into an adhesive, a wood welder vibrates one piece of wood on top of another while applying pressure. At just the right frequency, the heat and friction from the vibration melts the lignin at the wood's surface, as well as a little bit of another chemical called hemicellulose. The vibrations only need to last for a few seconds. That's long enough to heat the surface to above lignin's melting point, which is about 170 degrees Celsius. And it's also short enough to keep the temperatures below the point where lignin starts to break down into those smaller chemicals, around 280 degrees Celsius. The welding process also works if you screw a wooden dowel rod into a hole in a different wood block, like making a hammer or a wood lollipop. In either case, once the lignin cools down, it solidifies just like glue and bonds the two pieces together. Some studies show that wood-welded joints can even end up stronger than those joined with regular wood glue. And wood welding hasn't taken over large-scale production yet, but some researchers are looking into bringing it into applications such as furniture manufacturing. So with some careful physics, we get wood that melts just when we need it to, and we still get to enjoy our campfires.